Hey everyone, welcome to another episode of Robo Papers. Super glad to have Yuan Han with us today. He's one of the authors of this paper called FALCON, Learning Force Adaptive Humanoid Loco-Manipulation. Thank you so much for making the time, Yuan Han. It's good to have you. So maybe as a start, if you can share a little bit about yourself, how do you get into this space in the first place?
Yeah. Hi everyone. I'm Yuan Han. I'm currently a first-year master student at Humanoid University, advised by Professor Guan Ya. And also I'm currently interning at Amazon Frontier AI and Robotics team, led by Professor Peter Bell, Dr. Peter Chen, and Dr. Rocky Duan. And so currently I'm a applied science intern at FAR team. And previously I got my Bachelor of Engineer at Shanghai Jiangnan University in China, Shanghai. So yeah, and currently I'm mostly working on humanoid local manipulation. I also have some experiences on aero manipulation and some wheel-based mobile manipulation as well. And speaking of FALCON is basically so currently a lot of humanoid projects are focusing on lightweight tasks like pick and place or moving something really like not that heavy. So in this project, we want to investigate like push to the limits of how human what's the limit of unit G1 or boost T1 to like explore their maximum capability of doing heavy duty tasks in local manipulation tasks. Yeah, that's basically the background of FALCON. And I guess I can just dive into my project. Yeah, let me show the window. I don't know.
Easiest, I think.
The FALCON, the front-end learning force adaptive humanoid local manipulation. The motivation is like currently most of the work focusing on lightweight tasks. What if heavy duty tasks? I think it will bring challenges to both like upper body manipulation as well as lower body locomotion. Because as you can see in back to 2015, the DARPA challenge. This is a robot trying to open a door, but the contact force between the effector and the door handle is kind of complex and unknown. I don't think that because at that time nobody used like learning-based method for humanoid control, so they basically use model-based method, and it's kind of struggle to do such a complex contact force task in this humanoid local manipulation controller. So it fails, and also this is for like the locomotion robusting task under significant unknown force. And as for the upper body manipulation, I also do a quick test on the current very popular method, which is upper body IK plus lower body RL. As you can see, with upper body IK, it basically cannot compensate the force. So there's a lot like tracking error for the upper body. So in FALCON, what I want to do is to make sure that my locomotion is robust enough and my manipulation, my upper body manipulation is precise enough under significant and unknown 3D forces on the end effectors. And our method is we propose a dual agent framework to train such a controller. So the insight behind this is that we actually try directly train with the whole body like monolithic whole body RL, but we found it kind of difficult to maintain the locomotion and manipulation performance at the same time. So what we want to do is separate the upper body and lower body signal, the reward signal, and let it train like two separate actor critics.
Yeah.
But if we directly
sorry,
train,
Johan, if I can interject and ask you, you mentioned that you guys actually try doing the monolithic whole body, like just one RL. And is it because you mentioned it's difficult? And is it because the exploration space is just too big, or like what are some of the difficulties that lead you to kind of do it like two different?
So one reason is the exploration, the height of action space. But another more important thing is I think some conflict happened between the reward signals. So let's say if you want to compensate, if you exert some force on your hands, if you don't compensate for that, let's say your upper body do not compensate, you just let the force like do push your arm, and actually at this time there's no counter force for the lower body. Well, let me put it this way. It's hard to maintain the stability for the upper and lower body at the same time where you are actually exerting the external force. It's kind of will behave like overcompensation. I can jump to the slides later, like here. So as you can see, the monolithic whole body aerial is kind of learn a strange behavior to compensate the payload on the hands, like the center of mass kind of shifting back a bit. But if you separate them, like
is that optimal though? The idea, or is this like actually just weird?
Yeah, it's just weird. I think monolithic whole body aerial can work, but you need a way more like reward tuning to make it behave is like
that makes sense.
Like what the fuck can do.
Yeah, I'm curious as to whether it's purely aesthetic or if this actually is like this. You think this works worse or is less stable?
Yeah, I think it can work, but just need more reward tuning. But if you separate them, it's way more easier and train way more faster. Yeah.
Cool, makes sense. Yeah, sorry to interject.
Yeah, it's a great ask questions anytime. And that's the basic idea. If we, but another thing is that we actually joint train those two agents to prevent like the dynamics feasible, because eventually we need to like influence those two agents at the same time. So at the training time, we also join train those two, and they are actually know each other's state because they share the whole body perception of the robot. And another thing is that we cannot just randomly add the force to the robots and effectors, because we need to consider the torque limits as well as the position limits. So another thing we do is that we calculate the maximum and minimum force that we can exert on the end effectors according to the current upper body joint configurations. So in this way, we just uniformly sample the force within the minimum and maximum force range. So in this framework, we enable efficient dual agent training and also torque limit aware 3D force curriculum to make it on the one hand, to make it can maximize the capability of adapting the external force while respecting the joint limit to avoiding some unnecessary training difficulties. And when deployment, we actually do both teleoperation and autonomy. And teleoperation is quite straightforward, just giving the commands through the joystick or Apple Vision Pro. And for the autonomy, I will address it later in our autonomy down. And we compare with the baselines, so both lower body IO, upper body IK, and monolithic whole body IO. So we find that, of course, our method outperforms them in terms of the upper body tracking performance and also the root velocity tracking performance. And this is the same result, like evaluate our policy trained in SI gym, but in Majuko. So basically, it can squat, it can turn your waist and do upper body tracking. We drag the end effector while stance is still stable. And this is kind of simulate the payload transporting, like giving the force along with the gravity direction for each hand. And this is simulating like dragging, for example, like dragging.
So two different robots here too. That's the booster on the right?
Sorry, say that again.
This is two different robots too, right? That's the booster, yeah.
Yeah, that's the booster. And another thing we found that very surprising is because we didn't tune any reward. The same reward setting can work for both Unity G1 and Boost T1. I think that's quite kind of surprising to me. But also it's reasonable because our like dual agent training is not that sensitive to the reward because you separate them and lower down the training difficulty a lot. Okay, and this is the real world results I mentioned before. So for the upper body, IK and lower body, IO baseline, basically the worst part is that it cannot compensate the upper body. So it just have some upper body tracking error. And for the whole body IO, it overcompensate and just didn't figure out a very natural way to compensate the upper body. Yeah, or both the upper body and the lower body.
So that's root tracking though. Is there like, do you have like a measure of like stability or anything like this? Like, is it actually less stable? Is what I'm curious about. Like,
yeah. It's for the whole body IO is really not that stable.
Okay. Yeah.
When doing local motion,
cool.
As you can see, the tracking error is the largest. Yeah.
Okay. cool.
So
Makes sense.
basically, for the lower body, our body IK has no force compensation for the upper body, and for the whole body baseline, it has like excessive whole body compensation. Yeah. And this is some of the demo. So first is payload transporting, and next is the stance pulling. It actually can stand at, I think the peak value of our force gauge is about 60 newtons. Yeah. And
So you can
it also
stand
has,
while pulling like almost 40.
not kgs, Newton. Yeah.
Sorry, Newton. Sorry. Okay.
Yeah. So you can also see it actually lean back a bit to
Mhm.
counter against your force. And this is car pulling. So basically here, the weight of this car is about, because there's one unit to G1 and one unit to H1. So the total weight is about 85 kilogram. And the booster tier 1 is only like, I think it's no more than 30 kilogram. So when you do baseline controller, like going back, it just barely moves, the robot barely moves. But when we deploy the FALCON policy, I think it pull the car very easily. I think I can add more, maybe one more unit should go to.
This is a nice video. Yeah, that's a nice visual.
This is like saving his comrades from the battlefield. Okay.
Yeah.
Okay.
And also there's a door opening. So as you can see, the baseline just knocked the door with his head. It's kind of funny. And for FALCON, just because FALCON can, we actually exert the force, like in our force curriculum, we exert the force like in harmony direction. So for the door opening demo, actually when you do the handle pulling, the force direction actually changing. Yeah, but still it can handle.
Sorry, but this is teleop, right? Is this teleop?
Yeah, it's teleop.
Okay, cool.
Maybe next is the autonomous. Oh no.
Okay, because that's very smart. Like change from here, and then you push, then you pull further.
Yeah, actually involves several pulling. At first is second is
do
pull.
that, and then you do that. Yeah.
Yeah, another one. Yeah.
Yeah. Okay, got it.
Yeah, I think autonomous demo is not the last one. Yeah, this is the last television demo. So we basically
I really like this one.
Yeah, I think this one is the best. Yeah. Do a tug of war. So according to this video, we can conclude that the boosted T1 is stronger.
Booster T1 is stronger. Yeah, okay. Pulling that.
I didn't know that.
Interesting.
Because they are trained with the same reward setting. They also, basically the training setting is the same, and we evaluate them and try to go back. The command is also the same, but boost the tier 1 win. Yeah.
It's also got a lower center of mass, right? So like that's
that
probably helps it a little bit too, right?
Yeah, makes sense. Yeah. And this is our autonomy demo. So I will explain a bit. So autonomy, we actually develop a hierarchical pipeline for the autonomy system. So the whole autonomy system is divided into like perception, planning, and control. So for perception, we use foundation poles to estimate, to get to obtain the grasping points on the two sides of the toad, and then the planning part just plan the upper body trajectory to grasp, and then the lower body and then the controller part just use the FALCON policy. Wait, sorry.
Very cool.
The planning handles the our body planning and also the locomotion, like from point A to point B.
Very cool.
And another thing to mention is the hardware limits. And I think I've talked about this like before Chris coming, like talking about the hardware, like the overheating issues. So one thing we found in this project is that Plus can actually handle like lifting up such heavy stuff, but the hardware stuff is not just that good enough. So when we actually reach into the model limits, like for example, the torque limits can only handle 3 kilogram, but here the bottle in our right hand is about 3.7 kilogram. So it can only, I would say, stands for 5 seconds and then just go soft. This is another big limit to our project, because I think if we have better wrist models, we can do way more impressive demos.
Gotcha. Yeah.
Yeah, that's pretty much about FALCON.
Cool. How long does it take to train these things? So you said that the way that you split up the upper and lower body was faster, but what does that mean?
Maybe just 6K iterations, I guess. 2 or 3 hours.
All that's nice. Okay, very cool.
Yeah.
Yeah.
Yeah, I've open sourced the training code.
Yeah, that's really cool. Could you? I don't know whether it makes sense to share like the paper, the PDF, but could you go a bit more detail into how do you do both upper body and the lower body RL? Like what kind of rewards you use? Because I think you use different ones, right?
Yeah, I didn't list the reward terms here, but I list some. Didn't list all the reward terms here, but I list some like important rewards to make sure that the lower body will remain stable while you're actually pulling in lateral direction. One thing is that I need to oh wait, I think I missed one term. All right, never mind.
Well,
Yeah, I think one important reward term is that I need to make sure my lower body's action is symmetric.
Interesting.
Because if you actually like random force directions, your lower body can actually learn very weird behavior to maintain balance. So one thing I add to the lower body reward group is the symmetric. So for example, I want the left part of the lower body and right part of the lower body, the actions are actually symmetric. So that's why reward term that really matters for the lower body. And for the upper body, is very straightforward. Just I want to track the target joint positions, and that's basically it. But I add another like the upper body's penalties for the large accelerations to prevent like very jittery motions for the upper body. And I think I also did several another very interesting baseline, which is I try to train a force estimator, because with force estimator you can just compensate the force with like model-based method like the inverse dynamics. So it works. As you can see, the figure 7, the figure B, the ground truth force and estimated force actually align very well. Their metrics, I compare the metrics in the table. Yeah, but I compare the performance of this like forced estimator-based local manipulation policy with FALCON, but it still didn't like perform better than FALCON. So I revisit this, and I have one explanation for this is that when you estimate the force, so you can only estimate the force that is exerted on certain positions, because in simulator we can only I think it's the problem of us at Jim, because we can only get the Jacobian of descent of descent of mass in each body link, so it can only estimate the force at that point. And but if you like do it implicitly, let's say you just randomize the force applied positions around the end effector and just let the policy implicitly infer how to compensate the force. So it doesn't care whether there's a little shift of your force applied position. But in here, we can only estimate the force at certain position. And if we apply force like in a slightly different position relative to the center of mass, then just doesn't work that well. That's one explanation for that.
That's interesting. Yeah, it's interesting to see that the more explicitly.
Yeah, basically just to compare like FALCON explicit to the implicit compensation.
Yeah. It's like the sort of like the dichotomy between like these world models that people are very interested in right now versus, well, I guess it is a very limited sort of world model because it's predicting just a forward dynamics model. But like versus the entirely implicit, just learn everything, and learning just works better. The simpler approach works better. As it often does. Yeah, cool. That's good to know.
Yep, I think.
Cool.
Let's see whether I have more.
So, so you were saying that you tried it on these 2 robots. Do you think it would work on a bigger one, like an Unitree H1? Because you said you didn't do any tuning to cross between these 2 different robots before. Like, as the robot's like mass and strength increases and height, do you think that would still be the case?
So the Unitree H1, I think I think for unitary H1, maybe is way taller and the center of mass is higher.
Right.
I think it depends. So let's say if you have the same strength,
Right.
but you are taller, then I don't think you can beat like in tug of war. You cannot
Sure.
beat
Yeah,
one
yeah.
that has one strength.
Well, I believe the H1's stronger, but I'm not actually sure. That's a good question.
Yeah, it's kind of a trade-off, like between your height and your strength. Yes.
Right. Well, for tug of war, sure, but like, I guess, does the method still work? Do you think that there's any like? Do you think that you would need to retune everything, all that kind of stuff? That was the. I know you don't know, but like, I just yes.
I feels like I need to tune several height related
based stuff. Fair enough.
Yeah.
Okay.
Like I need to like tune like the target feet high because you know smaller one of course have lower like target, no matter it's target feet high or target base height. Yeah.
Okay, I remember the other question that I was going to ask. Sorry, Michael, but like this was you were talking about the importance of symmetry in the lower body controller. One of the tasks is opening a door. Doesn't that involve asymmetry? Like one of the legs is going in the opposite direction from the other?
Yeah. So yeah, it's better. So of course, if you do cross stepping, like asymmetry, like cross stepping is stable. Is more stable. I agree with that. But it sort of just behaves not that naturally. What I want is that maybe you can act like you can have different actions, but your state, your joint position should like remain like symmetric, not symmetric.
So it still ends up. So I guess what I'm getting from this is that it still ends up being, it still ends up learning the right behaviors, even with the
Yeah, I'm just trying to think. So it seems that the manipulations are typically upper body driven, right?
Yeah.
But let's say if you want to train the G1 to play football, actually the manipulation is in the legs too.
Football is technically not manipulation. Right?
Yeah. Well, I mean, you're manipulating a ball. I mean, if you talk to Messi,
like kind of yes.
How would this change? I mean,
well, I think that's different task. So I think if you want to do football, then it's more like a motion tracking task because you want to track like your feet, your ankles. But here, it's more like classic locomotion. Yeah, it's because there's a lot of like recently I think Twist they show some demo like doing like kicking football, and that's that's all about whole body motion tracking. And here I think the task is kind of different, so it's focusing on some like more like doing because I don't think that the whole body motion tracking can do such stable locomotion like this. But if you want to transfer such a like the force adaptivity to whole body motion tracking, you can adopt the force curriculum that I proposed here to some like whole body motion tracking system like Twist.
Yeah. I mean, as a layman, I'm just thinking, I mean, one single body, human body can do, I guess, I mean, these are all different tasks, but it's all the same brain that's doing all these different things at the same time. I mean, I can play football while lifting, different 3 kg water bottle, 1 kg water bottle at the same time. So, yeah, I guess we'll somehow still some ways of what, I don't know, from maybe a more universal, like full body controller that can do.
I don't know if you noticed some recent paper about humanoid. A lot of papers they actually achieved very impressive results with one like single unified controller and one policy. I think the way they do it is that they have a lot of expert policies and they just distill, no matter distill into a diffusion model, just transform it. They just use several like MLP based expert policies that can do different tasks and trained with different robot settings, and then they distill those expert to a student policy, and the student policy have better like network architectures like transformer or diffusion model, and then I think that's one way to produce a very unified policy. Just learn from several experts.
But would those also be, as performant when it comes to like, all these force disturbances that we just, I guess, the focus of this paper?
Yeah. This paper just mainly focus on one, like I would say one task. Yeah. Do locomotion.
I guess what I'm asking is that like, because with those, that you just mentioned, those approach, well, they are not, whole body doing impressive stuff, but I'm not sure if they focus, like, I mean, if you have, they're subjected to the kind of force disturbance that you tried out in your paper. I wonder if those will perform as well as yours. Like, do you have a sense?
Actually, what I'm doing is similar to what I was saying right now. Just trying to add force to some like existing motion tracking training settings. Currently, my result shows that some of them do not work out of box. I think it may need more carefully curriculum if you want to adding force to some tracking tasks. So let's do one very extreme example. So if you want to do a motion like I also did ASAP with Thailand, right? So there's one motion we do Kobe Bryant like fade away.
Yeah.
So if you do that motion and you've actually, so let's say if you assume that the ball is super heavy, right? If you actually add like change the mass of your hand, I think that will definitely add a lot of difficulties to training that motion, because that motion is really agile and it even require the robot to like jump high enough.
Yeah, jump and then turn in mid-air and then,
Yes. Yeah, I think it depends on the task. But if you just want to do very simple like squat and pick up balls from the ground, and that kind of motion tracking training, I think is fine to add those force.
Yeah. Do you think like this, the way you set this up now, like with this dual agent setup, do you think it is, I guess, the final solution? I mean, versus let's say the whole body thing, or do you think it's just a better heuristic and therefore probably the one that should be performant for a long time to come?
Yeah, great question. So I'm also a reviewer of Coral 2025. I actually I reviewed 4 papers and 3 are humanoids, and 2 of them are using similar method, like decouple the upper and lower body. Yeah. So I think if you just want to do not that kind of whole body motion tracking like kicking a football, if you just want to do locomotion while you want your upper body can track any joint configurations, I think this is the best solution. Yeah, because it's training efficient and actually stable. Yeah. But if you want to do like some other tasks like this, let's say the whole body motion tracking, yeah, I think it's better to just train it as a whole body.
Yeah, I guess any other limitations besides the couple that you mentioned. So you mentioned about the overheated motors being a big problem. Is there anything that was surprising when you I guess one surprising thing that you mentioned is that you didn't have to fine tune for a specific embodiment, like you just work out of the box for both booster and unitary. Anything else that you was limitation that was surprising to you, I guess, when you were doing this paper?
Okay, so I would start with several limitations. So the first limitation is that I actually didn't show too much payload transportation demo, because one thing that's like one thing that stops this from happening is, of course, the hardware issue. But we find that even we try to do, I think I will share another screen.
Payload transportation, that means the humanoid carry something while walking.
Yeah.
Okay.
Yes. So basically the top left demo. So as you can see, the end effector is actually vibrating a lot when So I still cannot figure out why, but currently I'm trying to. So yeah, this is one limitation, because it seems that the upper body compensation cannot be solved. Like if you want to do a very heavy payload on the effectors while doing locomotion, vibrating a lot. This is one limitation, because eventually I think the most practical application of humanoid is just pick up a very heavy box, or like this, like 2 bottles, like payloads, and do payload transportation. It vibrates a lot.
I wonder if it's because, like in this case, literally the water bottle, instead of just having a consistent force, it's also like, it's got angular momentum in a
it
way,
has
swinging a
some.
lot.
Yeah. That's one reason, but this is not a reason why this. Yeah, this is a problem to solve. I agree.
Mhm.
Yeah, we need to like somehow stabilize even when your payload is not that like stable, not giving you consistent force. Yeah,
Got it. Yeah.
and another limitation is that it didn't. We only train Falcon on flat terrains, so the flat plane, but we didn't train on very complex terrains like stairs, right? I think what a humanoid, the really practical application, especially in the industry, is
Yeah.
that you can
That's right.
you can
Uneven
pick up
surface.
a very heavy stuff and doing upstairs, right?
Yep.
That's one of the advantage of the Lego robot.
Exactly. Yeah.
I think
Otherwise,
that's
this
one.
could have been a mobile base. Yeah, it's true.
Yeah. That's true. Yeah. I'm currently actually working on how to extend Falcon like on
Got
terrains,
it.
like stairs, like
Very cool.
close by the terrains. Yeah.
Yeah, but it's
And
interesting that. Sorry. Oh,
yeah,
you
go
have more
ahead.
limitations.
No, that's basically it.
Yeah. No, I was just gonna say, like, I mean, still, while it's flat surface, but clearly the surface, I don't know, just eyeballing it, it looks kind of slippery. So it's able to, like, still self-balance and while reacting to the force that's being applied, especially the tug of war one, right? They're constantly kind of slipping, but then recovering enough and then while pulling the other guy. So I think that's also really impressive already, actually.
Yeah.
I also thought one thing that I was noticing is that I think, like you were saying, there's tons of these papers of Coral and everything else that are doing this upper body, lower body stuff, but almost all of them use reference trajectories. You didn't, right? Or am I wrong here?
Yeah, it is not like a reference trajectory, just giving
Right.
command.
Yeah, this is nice. That's a very nice result. I think means like, I don't know.
Yeah, so basically you just train in simulation and then just straight away kind of apply to the real robot.
Yeah. Just currently seem to real. Yeah.
Nice. Very simple. Not simple, obviously, but you know what I mean.
Yeah, I mean, it's well, whatever works, right?
Yeah.
I also really like, actually, you have another demo video you didn't see, but where you have your, I think, carrying two things in both hands, but different weights. So I think one of it is 3 kg, the other one is like 1 kg or something. And it was able to balance.
That's why I think.
Yeah, so I thought that was quite cool as well, the video that you have.
Yeah, I think basically what we want to show is that we actually because we do not just add the same force on the both hand, we actually
this
can handle different weights.
Yeah.
Like, I think this one, right? Heavy lifting.
Cool.
Yeah, I think this really like maximize, I guess, the limit of the full humanoid. I guess, like, some manipulation task, if you do it the more naive way, let's say I don't know, lower body, upper body inverse kinematics kind of thing, then you're actually not maximizing what it can do, I guess. If you are trying to do some manipulation that actually it's quite a lot of force.
Yeah.
And so, I mean, like just opening up that door, I mean, it's this door, I mean, it's very, very common. So clearly, actually, the robots can do it, or rather the hardware can do it, but it requires just better policy, I guess, to enable it.
Yeah, this is it's for just explore like what this robot can get, like, and it turns out it actually can do something that like existing method cannot do, and also boosted UI is much more strong.
Interesting.
The ancient UI,
Cool. Yeah. All right. Cool. Yeah. Sounds good. I think. Do you have anything else you want to add, Yuanhan?
Any like any big takeaway? What's the number one lesson everyone should learn from this paper?
Well, first is if you just want to do such local manipulation tasks, then dual agent is better.
Agent is better. Okay.
Yeah,
cool.
dual agent is better than whole body, and is stable. Someone may question that the two agents, like the actions cannot work on, like, if you want to influence them at the same time, but it just turns out that it can work and pretty stable. This is the biggest takeaway from this paper. And actually, the fourth curriculum is more like a task-wise. For the general humanoids, I think the dual agent works better.
Got it. Yeah, I guess maybe a last question that we always ask, are there any recent papers that you come across that like kind of blew your mind or you want to give a shout out to? It doesn't have to be humanoid. I mean, it could be anything that piqued your interest. Could be something from computer vision,
Okay. One paper is I think it's one policy but many words. So this paper I think the paper somehow solved the problem of like humanoid working on multiple terrains. They didn't do real robot deployment, but the simulation results is already impressive enough. So what they do is that still they follow the like current trend, like training multiple policies for different terrains, and use a diffusion model to actually train a terrain encoder to be like make the policy terrain aware, and then distill from those expert policies. These one policies can actually just generalize to even the seen terrains and even unseen terrains, like the terrain combos. And this is one policy that I think is pretty useful. I think this a lot of humanoid people are currently, I don't think they are seem to real, but I think this kind of framework can actually do seem to real. Yeah.
Yeah, maybe we should get them off the pod.
Check it out.
Yeah, I should check it out. It's quite impressive.
Cool. All right. Very cool. Well, anyway, thank you so much, Yuanhan. It's been a really cool chat, and I really enjoy it. Some of the demos are really cool, especially the tug of war.
Thank you for invitation.
Very cool work. Yeah, thank you.
Yeah. Okay, cool. We're looking forward to your next paper then. All right. Thank you, Yuanhan.
Yeah. Oh, will coming soon in 2 months.
Oh, okay. Cool. Well, definitely. We'll have you on again for sure. Okay. All right. All right, Chris, what have you learned?
I thought this is really impressive work. I love seeing the robots doing tug of war. I think what's interesting is like we've talked to people like the twist paper and a bunch of these like robot teleop papers. So one thing in this is that they divide the upper and lower body. I think one thing, like first of all, like it works really well. It works cross-platform. I thought all the results are really impressive. I also thought it was impressive that he didn't take any shortcuts with training, like using like a lot of people use AMS, like humanoid teleop data or human teleop data to like seed or to get the motions to look right. They didn't do anything. It's just like pretty nice reward functions and just kind of works. It was nice. That was my takeaway. What did you think?
Yeah, firstly, I mean, this was a shorter podcast than usual because it was quite simple, like you said.
Yeah. Elegant.
Yeah, exactly. Yeah. Actually, yeah. Well, yeah. More, I say simple not in a derogatory, but literally like this. Sometimes the thing that actually work, like it's things shouldn't be
less hacks.
Things should be
just like it just does it. Yeah, I like that.
It should be as simple as you can possibly make it. But that's why I kind of like I pushed back a little bit on. I asked him a couple of questions about how does he think about this dual RL versus like dual agent. Basically locomotion manipulation are at the same time, like upper body, lower body, versus let's say the whole body RL stuff, which it seems like he's done in the previous work, because like you're basically still injecting humans like prior heuristics, right? In a way, right? You're defining, okay, you decided locomotion and I mean, but I suppose nature is just somehow there's just one brain that does everything at the same time.
Yeah, I mean, no, I don't know. I mean, our brains do have different specialized components, right? Like,
different parts of the brain,
right? Like I do think like this thing though, it does seem to all be one component, right? Like in our brains, but like our brains do specialize. I don't know. I don't know much about brains, so who knows?
Yeah. But I think the fact that we have two different words like locomotion and manipulation, and this means different thing. We understand the concept. Clearly, is a very, very good heuristic to have. So, and I think he just really lean into it and do it. And like I said, it's even he was a bit surprised that it kind of just walked out of the box, like for he doesn't have to do any specific thing between the booster and the Unitree, and both give very similar performance. So and I think it's really, I guess ultimately, again, as a non-researcher, when I look at these things, it's the demo in a way it matters in that it shows some newer capability that like. So I think his work really allowed the hardware to to show what it actually can do.
Mhm.
Actually, the hardware can do it, even though they are, the G1 and the T1, they are pretty. There's the smaller humanoid, right? But they can do quite a lot actually. I was a bit surprised on the booster T1 that it
Yeah.
was able to pull that 85 kg thing.
Mhm.
And he was saying that he probably can do it more, and I was a bit surprised that he can do that. So
Yeah.
so actually, the hardware can do it. It's the brain that that needs to be a little bit better. The whole body coordination and whatnot. So
Yeah,
it's
yeah. Well, there are other humanoids out there. Like, I'm curious to see where is he? Is he at like Nvidia now? He said he was in San Francisco. Like, he
no
should
no no.
try out.
He's interning at Amazon.
Oh, at Amazon. Oh,
Yeah
well,
yeah yeah
they've got digits. They've got real humanoids. They've got
yeah yeah
entries too. Yeah,
yeah
they got
yeah.
a bunch of
I'm sure.
robots.
Yeah
Or maybe they
yeah
don't
yeah.
have
I'm sure.
digits. I don't know what they
Yeah.
have actually.
Well, but I mean, this work
Yeah,
was done in like I guess when it's at
yeah,
CMU,
yeah,
right?
yeah.
So I think they
Yeah,
had
I guess. Right. Yeah,
yeah.
but I'm curious.
Uh,
Okay, cool. Good enough.
but I
Nice.
think two is already proved the
Yeah,
point, right? I mean, like I imagine it should be able to just like
yeah,
so long you have the simulation. I mean, so long you have the body in simulator, then you can do the same thing and then do this without it just maybe just work out of the box. So it's good stuff, man.
right.
Otherwise, yeah, I mean, imagine if you use teleoperation to collect data and then you realize, oh gosh, like, it can't do much, but then actually the hardware can do it. It's just that you didn't have a good enough
Yeah.
controller. So I think this helps a lot. Um, anyway, cool. Yeah, I guess that's a good
Awesome.
one. We'll do the next one soon. Okay.
Yeah, looking forward to
All
it.
right.
Yeah.
Yep.
See you.
All right. See ya, Chris.
Yeah.